One thing that I wanted to mention that went along with that whole conversion thing that like I said I was going to tell you, and then I forgot to tell you. And that is that, let's say you were in a situation where you did have that relief and you didn't want to increase the capacity. Looking at that chart again, let's go back to that chart for just a second.
Yeah.
So that extra capacity can help you, or you may not want it. So looking again at those two examples where you had the FG3 with the 100% capacity throttle plate that you're converting, and you put in the parts for an FG29, and you didn't want the 1420 because you did have a relief and you want to basically maintain the capacity so you don't have to mess with other components. Look, when instead, if I put a 75% capacity throttle plate in that conversion kit, look at the CG. It's identical to what it is when it was a standard port with a 100% plate. So that's close with all the throttle plates. You know, stepping down gets you close, and doesn't cause you to really go over where your original capacity was when it was a standard port. So that only causes one problem. What do you do with the FG3 that had a 35% plate in it, where you see that the CG is 380? How do you step down in that situation? Well, remember I mentioned that 25% plate, that 25% capacity plate that was kind of like special? Well, we have a bunch of them. We ordered a whole bunch just in case someone had this instance. So it's not published here, but you might want to make note of it though, that a 2-inch large port with a 25% capacity plate has a CG of 379. So you can just order the conversion kit with that 25% capacity plate. Doesn't cost any more or anything like that, just the same as the normal conversion kit. For the instance where you want to replace an existing standard port 2-inch that had a 35% plate and you don't want to increase capacity. Okay? So now we'll go back to the pilot stuff. All right, so back to this flow grid we're using as an example. We talked about the pilot being our brain, controlling the body and telling it what to do, and how we have it configured here in side mounting. We talked about the flow coming through the pilot, straight through, and loading on top with our loading line in place. And so we want to get into the details of, okay, but how is all this set up inside here, and how to basically maintain it? So we're going to break that down. All right, so this pilot actually can do 3 things. It needs one other external component to help it if it's doing one of the 3, but it can do pressure control or pressure reducing. It can be set up to be a relief. It can make this valve be pressure relieving, or just, you know, any kind of a back pressure control type function. And it also can do flow control. But in that instance, a mounted motor, like a Rotork motor, is mounted on top of this pilot and is adjusting the tension on the spring based on an external signal. So the motor is taking flow control input and is basically compressing the spring or backing the spring out to meet the flow requirement. So it overrides the only thing that the pilot knows to do, and that is to operate off of the sensed downstream pressure. So you can either have a flow control override, or you can just simply have it do flow control. You don't have to have the pilot sense anything in that case. So it can do either one of those functions as well. Okay, so they come in stainless steel or brass. They're both rated to 1500 PSI. They both have the identical spring ranges, regardless of whether it's stainless steel or brass. You obviously, would you want the stainless steel in situations where you're concerned about, you know, salt air, sour gas, things like that? Do you see that the added cost of the stainless steel would be worth it to you? Because otherwise, you know, it's not really. The one thing that I don't like about the brass pilot is just because they're these galvanized steel pilot bolts that hold the spring case onto the body, these over time tend to rust, whereas they put stainless steel screws on the stainless steel pilot and they do a lot better. You know, they don't get that kind of corrosion, which is why we're not like doing the steel restrictor and that kind of stuff on a normal Mooney regulator. But let's get into the details then of breaking this all down and looking at it by components. So to disassemble it, first of all, I would back all the spring tension off the spring so that as I take the body apart, it's not gonna be fighting me. I can take off this adjusting screw assembly, and these are sold like that, fully assembled. Old Mooney regulators, and you see that this has a roll pin in this top nut. That's so that if you wanted to replace the threads or whatever in here, you simply would push that out, take the nut off, slide the nut off, and take this lock nut off, and you can just run the adjusting screw all the way through and take it out and replace it, because it has a lip, a beveled head on the other end. So it has to come out basically through the top of the cap. But the old style, these basically would come right out in your hand. That didn't have that. So this was a product improvement from several years ago. We have some in our training stuff where when you back the spring tension all the way off, if you don't stop, the adjusting screw just comes out like in your hand. You got to thread it back in. Doesn't really matter. I mean, the spring case is not supposed to be under gas pressure, and it has its own vent. It has you know, a little vent port here. So it usually has a vent screen in it. So on this one, it's properly got the bug vent. Okay. So if there's gas coming out of that, then you got a leak in the diaphragm. So that's got to obviously be addressed. And it's going to obviously be affecting the valve performance because the pilot's not going to be able to properly use the sense pressure to work against the spring. And so what it's going to end up doing is, in a situation like that, it's pretty rare, but it's going to cause the valve to either fail open or keep going high, because you're not going to have that pressure underneath it to work against the spring to shut the valve off. Okay, so I'm taking the spring case itself off and out of the way. The values on these stainless steel screws, by the way, is also listed on the information that's on this tag. It'll tell you basically the limits of its pressure, 1,500 pounds, and it lists the bolt torque specification as 8 foot-pounds. So it's working to basically seal the top and bottom of that diaphragm right there. But what I'm after, what I wanted to get to so that we could talk about it, was the body. Okay, I'm gonna see if I can get this to zoom in so you can see, hopefully it's focused enough, where you can see on the bottom side it says inlet. On the top side, it says loading upside down. There, it's focusing. And then side to side, it says outlet and sense. So all the ports are marked, okay? If you look in this pocket of this, top to bottom, you see that the 2 ports for the loading and the inlet are right across from each other. And when I was describing the gas here coming straight through the pilot and loading on top, coming through and putting that inlet pressure. As soon as you introduce inlet pressure and this pilot springs back all the way off, it's coming straight through and loading the inlet pressure, whatever, 200 pounds on top of the diaphragm and keeping the valve shut. So it's not until I start to introduce tension on that spring to force the pilot to open it that there should be any gas flowing through. Okay, so you can see the physical path. And this cartridge has holes at that level, that mid-level right there. So that's the pass-through. It's just passing through, you know, on top of, or actually the way it's sitting upside down, under the orifice where the gas would flow up through and get out the outlet. So when the pilot's letting it dump, it's letting it dump through this outlet port right here. Okay, but until that happens, the gas is just passing through the cartridge. Okay, so take the cartridge apart real fast too. And it's probably high time that I mentioned one of those added values of this training, that you need a special tool to work on a Mooney pilot. Okay, it looks like this. Paper clip. Okay, that gives you the ability, find my special tool that I've already built, or I'll have to build a new one. Okay, I'm building my new special tool. Paper clip. All right. You need to get the orifice out of there when I'm basically doing anything with this, changing the O-rings. So I just gently push through the top hole where the little plug and stem assembly comes out, and I'm pushing the top side of that orifice, which is held in there by an O-ring. Okay, and the fact that it doesn't just come right out is good, because that means that the O-ring is doing its job. If it just flipping fell out of there, it's time to replace all the O-rings. And in a Mooney pilot, it's as easy as the body, except you just have 6 O-rings and you have a diaphragm and a plug and stem assembly. That's your entire pilot rebuild kit. Okay, so then you can see deeper in the pocket of this. Let me get it where you can see it. Down deeper in the pocket on the bottom, you notice a hole, and that's with the outlet port. Let me get this thing. See how it's the outlet. So what's happening there is when this thing is sitting inside the Mooney, this is the orifice in the cartridge right here. Okay, this is the plug and stem assembly. It has a little popsicle stick with a nitrile plug on it. It's sitting in there like that, and the gas is flowing underneath it through the inlet, through the restrictor, and loading on top. So the gas never can come up through that orifice because it's plugged. Okay, when the spring on top pushes down, it forces that little plug and stem assembly off of its seat. Forces it off of its seat, and gas can flow up through the orifice and out the outlet. That hole I just showed you in the outlet is where the gas goes that was on top of the spring case, was on top of here. Now the gas is going to be able to dump out through the outlet. Okay. And remember, I mentioned the importance of the restrictor. If this isn't here, it doesn't matter that the gas is flowing out through that outlet, because it's just going to load back. It's just as fast. So I need this component and its ability. I can adjust it so that I can make sure that the pilot dumping gas through the outlet off the top is happening at a faster rate than its constant attempt to reload it. Okay. I want it to constantly be reloading because it gives us responsiveness. It means that as soon as the pilot says, okay, that's enough, it's already trying to do it. It's not something that one thing happens then another. It's constantly happening. And the sensitivity of that, or the stability of the regulator, is being determined by how much of this is happening to fight against what the pilot is wanting it to do. So what the level of balance is, okay? So back to our little components here. Sit down. Okay, I've got my four ports that I mentioned, but we didn't talk about the one that was the sense port. It's because it's not in that pocket. It's not in here, okay? It's this little hole on top. You see a little hole on the 12 o'clock position there. That's where the gas from the sense port downstream is coming in, under the diaphragm. Under that. Pushing up. against the pressure of the spring that's being compressed by our adjusting screw assembly. Okay, as that goes down, it's got a little follower on top, and as I crank it down, it's compressing it. Okay, forcing that plug and stem off of its seat. So it's up in there. That's the plug and stem sitting up in there, and you see it's sticking out. So when I compress the spring, it forces that down and opens the valve. It opens the pathway for the gas to dump, which opens the valve. Okay. When the pressure on the underside through that sense port right there gets great enough and can basically balance against what that spring tension is, the little springs that are in the pilot, these little ones that are on the underside of the pilot's plug and stem, they push it back up in place. So it comes back up when it has the help of the sense line downstream pressure to work against the spring. And then that closes the valve. Literally all the function that changes from the regulator passing 200,000 cubic feet an hour to zero is happening within an eighth of an inch of a little plug and stem assembly moving up and down. It's incredible. I'm talking about how this serves as a brain and amplification chamber. That's exactly what I'm talking about. Okay. All right. So to do what we want to a pilot, let's say we're just doing periodic maintenance. Okay. And I mentioned there were 6 O-rings. One of them is the little O-ring on the orifice. So I got an orifice O-ring, and I got a little washer that basically keeps it in place. It sits on top of it. And when I put this back together, that all goes in there together as one unit. Okay, so I've got that. Orifice number 2 is on this bottom cap. Okay, so, and they're all basically different sizes, so it's easy to like take one off and put the right one on. So that's just keeping gas pressure from escaping out the bottom of the insert assembly. And I want it to pass through the insert assembly. Another one, and it's not even a gas seal, it's basically a weather seal, is on the underside of this adjusting screw assembly. The reason it's not a weather seal is we already talked about there being a bug vent in that spring case. So there's atmospheric pressure in the spring case with the spring. So this is just keeping rain and stuff out of the top. Yes, this is pretty tight, but I mean, that's not a gas seal either, where the adjusting screw is moving in and out. So this lock nut does have a rubberized bottom, but it's not intended that it's going to hold back 200 pounds of pressure or something. So this O-ring is probably the least of your worries ever. Okay, so that's 1, 2, 3, 4, and 5 are right here, the top and the bottom on this insert assembly. It allows you to divide the chambers. You got the middle chamber, which is those holes that's allowing the gas to flow underneath the orifice and the plug and stem assembly and load on top all the time. The top holes, which let the gas, when it comes through the orifice, get out to the outlet and flow to the downstream side and combine with the downstream gas as the valve opens. Okay, so I've got those 2. And my final O-ring, not to be forgotten, is the little one in there. It's called a stem O-ring. Okay, it's what keeps the gas between the outlet gas that's dumping and the sense line gas here from combining. Okay, so it's a seal as the plug and stem assembly moves up and down. Okay, so if it just comes out, on that when I pull this assembly out, that's like the canary in the coal mine. If your little stem O-ring comes out on the stem, time to replace all the O-rings, because it didn't hold up in place where it's supposed to. And if it didn't, that means probably the rest of them are ready to go too. So I would replace them all. And it's a real easy thing, you know, just to pick it out. You can just use a small little screwdriver or something if it doesn't come out. And it's real easy to put back in too. I'll show you that here in a second. Okay. So that's my O-ring number 6. And so when you get a rebuild kit, how many O-rings do you think you get in a pilot rebuild kit? You get 9. Okay, so yeah, so that I need some explaining there. All right, so let me get a pilot rebuild kit. There it is. One of them is really good news, by the way. The other 2 are ridiculous. Okay, you get a little bag with all your O-rings. Like I said, there's 9 in here. You can kind of see if we pan down what we've got. All right, we've got basically, there's your stem O-ring. These 2 are the ones for your cartridge. This one is the one on the top of your adjusting screw assembly. You have one for your orifice, which would be that one. You have one for the bottom cap right here. Okay, and then you got these 3 that don't seem to belong anywhere. Okay, this one is for a high pressure pilot. Okay, so if we talked about before when I had that up there that you can get up to 900 PSI out of a Mooney pilot set point. But when you go through the different spring ranges, you don't see where that is because the typical springs for a Series 20 pilot are red 3 to 12, plated or silver is 4 to or 10 to 40. The blue is 25 to 90. The purple is 60 to 200. 2 blues here. The black, which is 100 to 260, and a green, which is really white with green stripes, is 200 to 450. So the way you get to 900 is you have to put in a spacer. This is what the spacer looks like in one to complete. This is a high pressure brass Mooney pilot at FP42 that has the 400 to 900 PSI rating. And you notice that it has a spring that calls that out right there, green spring, 400 to 900 PSI. Okay, so how I get there? This is an example of a conversion kit that allows me to convert the regular pilot to the high pressure version. And I can only do that with the ones that are a green spring or a black spring. This is the spacer assembled that goes in there. Okay, it has a new diaphragm, a high pressure diaphragm, a spacer, an O-ring, and a place for the spring seat right there, and a little nut holding it all in. Okay, so when I put that down like that, okay, it replaces what came out of it, which looks like that. That was the original one. Okay. Now, instead of having the diaphragm seal top and bottom, now I have the diaphragm seal on the bottom of the body, but I have an O-ring on top that seals the spring case right there. That's that O-ring, okay? So, and this allows me to double the spring range of these 2 springs. The black now becomes, instead of 100 to 260, 200 to 520. And the green one, instead of 200 to 450, is now 400 to 900. Okay, by putting that spacer in there. So in the little kit, I get a new spring sticker, and all the components to make that spacer work. Okay, so you don't have to build, if you don't have to buy a high pressure pilot, if you don't want to, you can just buy the conversion and make your own high pressure pilot very easy. All right, so talking about these other O-rings. This O-ring right here is for the lever assembly in a pilot we haven't talked about. This is what the Series 20L pilot looks like. Okay, You can see that the insert assembly is offset and it's made of aluminum, but it's the exact same components, exact same O-rings, exact same plug and stem assembly are in this cartridge. It's offset by a lever because you got a bigger diaphragm here, which you see in situations where you're trying to control really low pressure. So to make fine controls, the surface area needs to be bigger. And so this 20L pilot takes the place. And it uses springs that go down to 5 inches water column. And it would just basically take, in any configuration on a Mooney regulator, any size, you would use this anywhere where you want to set between 5 inches water column and 8 pounds. So there is some overlap, okay? The springs look a little longer and lighter. These are 3 examples. The brown one is the 5 to 15. The white one is 10 to 40 inches. And the yellow one is 1 to 3 PSI. So beyond 1 to 3 PSI, you can go back to the standard series 20 pilot, because this one gives you, in the regular pilot, 3 to 12. Okay. So that O-ring I just mentioned belongs in that lever assembly that I said, because you offset this, so you don't have it in a normal pilot. I don't know why you get it in every stinking pilot rebuild kit. It makes no sense. Okay, but that's where it's intended. I think it's for the ease of them, you know, having somebody, you know, somebody untrained, doesn't know your job like you, fill in the bags so they can just give them every one, and that way they don't mess it up. But anyway, that's where those 2 go. There is the third one though, this little one right here. Okay, that thin one is put in there because it's the orifice, it's like the orifice O-ring that goes on that stainless steel orifice. Sometimes though, the orifice is not this stainless steel material. Sometimes they use a Delrin orifice, and they use a plug and stem assembly that is all stainless steel. The plug and the stem, I should go grab one on my break. It's all stainless steel. It's not nitrile plug and stainless steel stem. It's stainless steel, and the orifice itself is a white plastic they call Delrin. They do that when they go to reliefs, high pressure reliefs with green springs. The reason they do that is because if you have all that spring tension cramming that nitrile plug down in that stainless steel orifice for years, waiting to relieve, it deforms that nitrile plug to the point where when the relief finally goes off, it don't want to reset in the same place. It's just caused a huge change in its shape. So the way that they avoid that is they'll take and make the, you call it the soft component, which is still a real hard plastic, but it's a white Delrin, is what the orifice is made of. And then the hard component is now the stainless steel plug that sits on top. Now, when it goes off and reseats, it's got a lot cleaner, a lot more perfect reset. So when that happens, which you probably don't have any that are like that, but when that happens, because the Delrin has to be made to handle the same pressure as the stainless steel, it has to be kind of fatter. And so the way that they make up for the fact that it's fatter is the outside diameter of that O-ring I just showed you is the same for the let me see this. The outside diameter of the orifice O-ring are the same, but you can see that this one's thinner to allow for the Delrin orifice to be fatter. Okay. So again, under some circumstances, you would say, well, I don't need that Delrin orifice then. That doesn't even have any of those. But you do have restrictors, and it's the exact same part number that basically helps you to rebuild a restrictor. And you have to have a restrictor. So let's talk about the restrictor next, real quick. Okay. Try to get down there where you can see me. Remember I said there were 2 styles of restrictor, okay? Whether it's stainless steel or the wash steel. You got your Delrin. Thank you very much. Got Cavalry coming with a Delrin orifice and a stainless steel, all stainless steel plug and stem. That's not the right one. All stainless steel.
Oh, you just want
The Cavalry's leaving. I want a Delrin orifice and an all stainless steel plug and stem. All right, more on that later. Okay, so what you have inside this restrictor, because I said that it's basically like a tiny little valve. It has a graduated slot in the on the drum, on the rotor, okay? And when I put that in, and by the way, notice the O-ring right there. Guess what O-ring that is? It's the one that you're not using, or one of the three you're not using in that rebuild kit. So if you save the extra ones that you don't use when you're rebuilding your pilot, all you need is 2 pilot kits and you can rebuild your restrictor, which doesn't have to happen hardly ever. And you're going to save a lot of money, because they think that those O-rings in a restrictor O-ring kit must be made of flipping gold, because they charge like $45 for 2 O-rings and a bottle of lube, which is, it has like 1/5 or 1/10 of what is actually the space in the bottle or in the tube. So don't buy them. Buy just the rebuild kits, and then save that O-ring, and you can rebuild these restrictors. There's 2. The one that didn't come out when I took this apart is still in there, okay? One on each side of the drum, and when I put it back in, then they're held in place on the other side by this little thread in end piece. And one, it just goes, just to tight. They got a little slot screw so you can hold the head and screw. And then you can see that it has a graduated scale on there. Okay, so let's talk about that scale real quick, and then we'll go back to this rebuild of the pilot. It says min and max. Okay, so the top says max, the bottom says min. All right, so what that corresponds with is the size of the hole on that graduated drum that actually can let gas pass through it. If I put this thing on max, the space, the hole through it, if I held it up to light through there or whatever, it would be the biggest, okay? I could see light through there pretty easily. If I put it on the min, the hole is just as small as it possibly can be. In fact, if it was any smaller, it'd be a way that I could fail my valve open, because it would prevent any gas from getting through there into the loading, top of the loading line. And it literally, if that was the case, if it wasn't just long enough to have a super small pinhole, when I slid that to min, it would immediately fail the valve open, because no gas would be able to pass through and load on top of whatever the inlet pressure is, which is how the valve is closed, right? So give you an example of how that's useful information. It comes, first of all, with this set on 4, the mid-range, and you usually don't have to mess with it at all. But let's say you're in a situation where you've got a worker. All right, now we're in business. Okay, here's what we're talking about. Okay, that's the Delrin orifice. That's the all stainless steel plug and stem. But it's normally going to be set in there like that, with the orifice plug down from the top, with the spring tension holding the relief set point. And then it's going to take that inlet pressure, the pressure from the upstream side getting high enough to work against that spring tension to cause the little springs on the bottom to let the plug and stem push up, and the gas will flow through. It's just that the block, the seal, is on the opposite sides, on the top instead of the bottom. That's how it gets set for relief. Okay, like that. Okay, and that's why. So you can set, Mooney regulators without those components as reliefs all day long, but when you get to those really heavy springs, you probably are going to find you want to switch to the other materials so that you don't get that issue with the plug basically mushing itself into the hole. over years. Okay, so back to the restrictor real quick then. How this is handy information. If I put that, and we'll go back to this regulator view for a quick moment. If I put this thing on min and I made that hole really, really small, what I would expect that does to this Mooney is now I've got just a little bit of gas that can make it through here and try to load on top, which means that as soon as the pilot tells the valve to open because the downstream pressure has dropped, right? As soon as that pilot senses that, because the spring is winning now that we have set, and it's opening the valve and causing this pressure to fall off, it's going to happen really fast because the normal flow of gas that's trying to reload is much less by volume than the stuff that's able to dump through that orifice. So it's going to open quick, and it's at the time when the pilot then reaches its set point and it wants the valve to close and reload and close that off, it's going to happen slower. So it's going to open faster and it's going to close slower. All right. Now I put it on a bigger number. Say I put it on 5 instead of 4, or something like that. I've made the hole bigger. Now I've done just the opposite. When the pilot says, okay, I'm sensing less pressure downstream, which means I need to open the valve, the spring starts to win out, the pathway to dump gas from the top opens up. Well, there's a ton still trying to reload because that hole's bigger. So it's going to open slower now because it's having to combat more of that gas working against it. But as soon as the pilot feels the set point is reached, it's going to close like lightning because it's got all this gas pressure that's always constantly trying to get there, ready to do it as soon as there's no place else for it to go. So bigger numbers mean open slower, close faster. Smaller number toward min is it's going to open like lightning and it's going to close slow. So what's the problem? So let's say my problem is I've got my monitor is really close to my MAOP, and I want to make sure that I'm giving my Mooney regulator the best possible chance to lock up as close to its set point as it possibly can, so it avoids getting close to the MAOP. Well, if I put that on a bigger number, it's going to help my pilot when it senses that it has to shut the valve to do that, because there's going to be a lot more gas available to get it shut. What would be the typical parameters that would be acceptable for a pilot when it comes to lockup? Well, a Mooney pilot will lock up between 1% and 2% of its rated set point. So let's say my downstream set point is 100 pounds. That means by 102, I should expect to see lockup if I got everything set up right. If it's at 1,000 pounds, or that's actually beyond the normal spring range, I have to use an FEP pilot, but let's just say, then it could be between 10 and 20 pounds before it finally locks up. Okay, so 1% and 2%. The closer to atmosphere that the actual set point is, the tighter I would expect it to be. All right. Any questions on any of this so far? Anything coming across that someone's asking? Okay. Is anybody that's listening to any of this, is this good information? Is this helpful? Okay, assuming so, I'm going to demonstrate something about that restrictor to kind of give you an idea of, because the Mooney regulator, we said, is primarily, we're speccing it for gas because we're gas measurement and regulation gurus, so to speak. This is where we see this thing being used most of the time. But if it was regulating water, it would still work. And just to prove that point, I've got a cup of water. This is my Bill Nye the Science Guy portion of our training. Okay, I've got this restrictor. This one happens to be steel. All right, I'm going to set this. I'm going to set it on min. So my hole's really, really, really small. Okay, and I'm going to, instead I have actually some natural gas I can spoon up. So I'm going to use water. I want to basically pour that into the inlet. Okay, and you can see that's about the rate that water can pass through with it set on min. Dun, 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 dun. All right. Now, setting it on max. Okay. Put my water in. See that? Blew through there like shit through a goose. All right. So anyway, that gives you a way to be able to visualize what's happening in that restrictor, okay? Okay, back to this pilot. All right. Now, when I'm doing my normal rebuild, getting my high pressure spacer out of the way, I'm going to have to replace this diaphragm. So I take off this nut, push the little retaining bolt out, take the little spring seat off, and I get something that looks like that. Okay, so you can see where the ridge is on that. Okay, this is out of the rebuild kit that I just tore everything out of. Okay, so I'm put a new one in that has that ridge in the same place. That ridge allows the seat basically to sit right down there in kind of a pocket where the ridge kind of like forms the shapes around that angled shape of that seat. Okay. Now, if it's a high pressure pilot like this, I've got the spacer on top, so I don't want that ridge in the way when I build that. So the difference between a normal pilot rebuild kit and a high pressure pilot rebuild kit is only the diaphragm. So you do not want to use, this is like the standard port, large port diaphragm thing. You know, you don't want to use the wrong diaphragm. This is what the high pressure pilot diaphragm looks like. Notice where the ridge is moved real close to the center as comparison, normal one, high pressure one. And it's so that this ring, this spacer ring will, let me take it off so you can see it. Okay, so I got my high pressure spacer. I got my diaphragm. So ridge facing up. Now the ridge sits inside the spacer, and I've got a clean sealing surface all around where the spacer's meeting the diaphragm underneath. I need a little bit longer seat to put down so that it'll actually reach the diaphragm. And then I can put together this little diaphragm sandwich. So I put the stud through and my nut, and I rebuilt that portion of the high pressure pilot. So the only difference in a high pressure pilot's rebuild kit and a normal pilot's rebuild kit is the diaphragm's different, and I use that big O-ring they gave me. I use it because before I didn't, okay? So there are two part numbers, but the only part that changes is the diaphragm. So let's say you were in a pinch and you had a situation where you had a high pressure diaphragm, but you only had regular rebuild kits. Well, just take the regular diaphragm out and put it in, you know, the bin for later. Use your high pressure diaphragm, and you got everything else you need to build the high pressure, rebuild the high pressure pilot. Okay, so now we're going to put this thing, assuming we've done all the other 6 O-rings that I described, replace those. Now we're going to put this back together, this insert assembly. Okay, so it starts with my little, I call it an Oreo cookie sandwich because it's opposite colors, but gets the message. So you got your stainless steel orifice. I've got my stainless steel orifice, or my orifice O-ring that goes on the stainless steel, the thicker one. And I got that little washer that goes on top. So I've built that. Then I take my normal plug and stem assembly and I just drop it on like that so the plug's facing up. Now I can feed that whole thing up through that hole till it sticks out the top. And then I can flip it over before I let my thumb out of the way because I don't want it to all fall back out, and I can leave it in there. Now, you can see this part is called the stem guide. Okay, the fat side goes down against the fat side of that plug on the plug and stem assembly. And it literally is making sure that when the stem is moving up and down, that it has that guide to basically be a steady pocket so it doesn't get off kilter and get where it's angled. Okay, I want it to run true north-south. Okay, there are two parts, two springs that go in there next after that guide. This little one right here is basically to ensure that that little spring guide has tension up against the, you know, the underside of that plug all the time. And the fat one, that's called the return spring because it's constantly trying to return the plug and stem to its home seat when the spring on top of it's not forcing it off. And then this is the one that's actually pushing up against the orifice body itself so that the orifice can't back out and come down towards the plug and stem to meet it. So those two just drop in there, skinny spring, then fat spring, and then I cap it. So I just put the cap back on, and that holds all the goodies in there. And when you rebuild this, you're gonna feel like a little pop where that orifice O-ring that we had to use our special tool, i.e. paperclip to get out, gets back in its seat, and you feel it actually like lock into place, I guess, for lack of a better way to say it. Okay, and I get the plug and stem assembly standing up there about 3/8 of an inch, and I can test it. I'll push down, I'll feel it go off its seat, and then if I let go, I should feel those that return spring push it back up against the orifice, the bottom of the orifice, and lock it back. Okay, so that's a properly assembled cartridge right there. And then you can put it basically back in, assuring that your stem O-ring is in there. Well, how do you get it back in there? Well, all you gotta do is put it on the stem like that, and it will find its home. So you just push it, start it screwing in, and screw it down. And it will lock that stem O-ring in place. And you'll see then, once I'm done, that I've got the stem just sticking out the top a little bit like it did before. And if I take this out, I fully expect that stem O-ring to stay up in that pocket that it belongs in. Okay, and it did. Okay, so that's what you do about that. And then the other building is just taking my, you know, my diaphragm and my components to ready that to put the spring on. And that's a real fast, again, ridge up, the plate, the diaphragm seat in place there, put the stud through, lock it in place with a nut, and then you hold the bottom where it is there so you're not gonna like pinch the nitrile, and just tighten it up, and then just lay it on there. Now you can put this vent port, usually it faces the sense line, but it's not essential. It's wherever is convenient for you. And if it's like mounted on the side or something, obviously you're gonna pick a place where it's facing down, or you can put a 90 in there to keep the weather out of it. You know, you get freezing rain sometimes, it freezes at night, and if there's moisture in there and it gets in that chamber and basically does like a you know, flash freeze of the diaphragm, it's going to affect the pilot being able to move the diaphragm, and therefore the valve's not going to work right. So another reason maybe to keep it warm, or at very least keep that vent facing the downward direction to keep any chance of moisture getting in there in those situations where you got like driving sideways rain and then it freezes. Okay, once I got that in, I can put my bolts back down. Once I do that and put my spring in, my follower, right there with, and that, I've found people that put these in upside down for some, I don't know why reason. It naturally fits just in the center of the spring and gives this little rounded end of our adjusting assembly a place to kind of like run true in the center. So why someone would stick it with a pointy end up, I have no idea, but you're going to change the spring range if you do it, for one thing. And literally, if it's like a red spring where, you know, a lot of compression is required to get the full value, you've just changed what you can get out of it. Okay, so that's not good. Anyway, so that's all there is to that. One more thing I want to talk to you about then on the pilot is, what if instead of making this a pressure reducing valve, I want to make it a relief? Well, literally, there's only two things required to make this a relief. One is I've got to change the orientation of components in my pilot cartridge. Okay, so I have to redo basically the order of assembly of this. All the same parts, I don't need any new ones, just change the way they're in there. The other thing I got to do is take my sense line, which was normally pipe downstream, right? 8 to 10 pipe diameters at least. I want to get, and what, by the way, while we're at that, people will come up with a question. Well, you know, what's the important things to consider when I'm talking about my sense line? Well, the reason that it's even an issue is as gas comes out of the outlet, it's just come through that throttle plate, high velocity, and it's churning. You know, there's a certain degree of turbulence being created because it isn't just a straight pipe that a bullet form pattern, you know, is created and moves in a very predictable way. We've got gases coming out that is churning, and there's a lot of fluctuation in, you know, the way that would be sensed by the pilot. So we want to get away from the body a little ways, let that gas kind of calm down a little bit, you know, create more of a laminar pattern at least. And if we had, I don't know, like 25 pipe diameters, a perfect bullet pattern would form again. If it was just straight pipe, that nothing was in the way, no valves, no other components, no changes in pipe direction, no changes in pipe size, you would get that. Okay, well, the good enough is you get away from this 8 to 10 pipe diameters with nothing else creating turbulence, and you're going to give this pilot enough room to sense the pressure that's downstream in a way that it can control within its parameters of that 1 to 2%. Okay. Some of the things to consider: you have a fast acting load, some real high demand that this regulator is feeding, asphalt plant or something like that. When they go to high fire, it just pulls the heck out of everything that's downstream of this regulator. Well, one of the things you can do to help this regulator, I mean, it's fast acting for sure, and I could make it faster acting by reducing the number on my restrictor, right? So I'm gonna get dumping and opening quick. But if I can place that sense line closer to the load where it's being pulled from, then I'm going to give the pilot an earlier notice that, hey, this is coming and you better start opening. Okay, so it's going to give better performance in that instance. So that's another thing I got to consider with placement of my sense lines. Anyway, so that's that. Now let's make it a relief. And I said that to do that with a relief, I'm kind of thinking about the same things about giving my pilot, ample room to know the pressure. But now I'm worried about when my regulators that it's protecting have failed to hold the downstream pressure where they are supposed to. We want to keep it below the MAOP. So I'm going to expect this relief to open before I reach that. So I'm going to set it at a set point that's going to protect the system and vent that to atmosphere. So I set my pilot to know upstream of it on the, the relief stack, what that pressure is. And now I need to change the cartridge. So I'm looking in the right direction because I put my sense line in the right spot. Now I'm going to get back into this cartridge. Notice, by the way, the spring on the cap on this says PRV. Okay, well, it's going to need to, if I'm changing it from pressure reducing valve to a back pressure mode, then I'm going to want to change that spring too. So someone, again, it's kind of like the capacity tag on the body, knows what mode this cartridge is supposed to be in. And it's really easy to check, but why have to get into it and, you know, have to blow down everything so I can get the cartridge out just to do that. So shouldn't have to do that. I have to go back to my Mooney tool. I have to push that orifice back out. And again, I'm just easing it around because it's one of those things where it's because of that washer, it's got to come out kind of like perfectly lined up. So I'm just kind of like working it down and out. I don't want to like push real hard from one side because it's just canting it in there. It's not going to help me. Okay, I just want to nudge it out in a straight fashion. Okay, when I get it out, I don't have to take away my Oreo cookie. I don't do anything with that. And remember, that's the way I put it in when it was pressure reducing with the plug facing up. Now I drop it in from the top, plug facing down. Okay. Now I feed it the same way. Push it up in through that hole. Drop it over once I've got everything in there, and everything else goes back the same. The little stem guide, fat side down, drops on the stem. My return spring, the skinny spring, drops on around the guide. And then my orifice spring, the fat one, goes down around the return spring. And I put it back together. The one thing you'll immediately note when you do this is the stem sits higher now by, I don't know, it's about almost 1/8 of an inch, probably between a 16th and an 1/8 of an inch, but it's noticeably higher. Let's see if I can show you. Okay. All right, so that is the one coming out of this valve that we're playing with. This is the one that I just rebuilt as a relief. Notice that difference. Okay, so, and by the way, someone asked the question, can I put a stainless steel cartridge if I had it in this Mooney Pilot, and will it work? Well, yeah, not a problem. You know, the typical thing is when we're worried about dissimilar metals is things like aluminum, you know, or steel bolts that aren't coated in an aluminum meter can create a corrosion point. And when you go to unbolt the meter later, you're taking the aluminum threads out with it. Well, you're not going to have that same kind of a crisis with the stainless steel and brass, but so you could use that in a pinch, but that's more expensive than this. So I don't know what you're doing with you, unless you just have this handy. I don't know why you do it. Okay, anyway, so I put that back up in the Pilot, just like we talked about, thread it back in. And now when this green spring is working on that, or whatever my set point is, when it's working on that, it's holding that down and forcing it on its seat. Remember, the plug is down on the orifice from the top now. So pushing down instead of opening the valve is keeping it shut. And now when I get that inlet pressure being too high and working up against that spring, it lets it pop off. So I'm feeling the same thing, but now when I press down, I'm holding it on the orifice. And when I let off, I'm feeling the springs force it off. And that forcing off will let the gas through those holes on the top, out the outlet, and the valve will open and the valve will relieve. Okay, so it's as simple as that to make it a relief. I changed the orientation of the components in the cartridge, and I changed the position of my sense line. Okay, I think we're at another point for a break. What do you think, David? Another 5 or so? Okay, before we get into the Flomax, which is something else that definitely I think will interest you, I wanted to backtrack just for a second on this discussion about the pilots. Notice this ring right here. Okay, this is the high pressure pilot with the green spring that I mentioned earlier. All right, so you see the spacer, you see that ring. Okay, so that ring prevents me from crushing these heavy springs, whether it's the black or the green, so that they'll break because they're so stiff. So I don't want to like crank down on that adjusting screw so deep that it actually would cause that to snap. All right, so on a black spring or a green spring, whether it's high pressure or not, this anti-crush ring is there. And if there's not one on there, or you change springs and you don't need it there because you want to get the full range out of the spring, which is the opposite issue if it's a light spring. Remember that roll pin, just take the roll pin out, take the nut off, either take off or put on the anti-crush ring and put the nut back on, push the roll pin back on, easy peasy. Okay, so that's something to look for when you're looking at your spring ranges. If it's purple, blue, plated, red, it should not be there. If it's black or green, high pressure or not, it should be there. Okay, so here's a pilot on this Flomax that has a blue spring in it. Notice that it's absent. Okay, same thing on this flow grid. Okay, no gold dwarven wedding band right there. Okay, so anyway, all right, on to the Flomax. The Flomax regulator is, as its name implies, capable of a lot of flow. All right, so think of it in terms of this. These two regulators are both 150 class, this one being an FT29, this one being an FM1 2-inch Flomax. This one with 100% capacity plate in it had a CG of, which we had a way to quiz you, I could give you a prize, 1420 on that chart that Drew shared with you, okay? This one with its 100% capacity plug retainer installed has a CG of 2250. So it would enable you in many cases to use a 2-inch valve where otherwise you would have to bump up to 3 to get enough capacity through it. It's fantastic there. But even better, remember where we talked about this one not being good when you're making shallow pressure cuts, 5 pounds, 10 pounds, and such, or you wanted to do a relief and set it at 5 or 10 pounds. Not a good solution for a flow grid, but the Flomax will go full open with 3 pounds of differential pressure. So, and that's in the 2-inch size. When you get up to the 4 and the 6, it goes to full open and 4 pounds differential pressure. But you get the point. I mean, it's going to be ready to give you a lot of flow in a relative instant. Double-edged sword always with flow and pressure. Why we didn't want to use these drill hole and step drill hole throttle plates when we didn't have to use them in a flow grid is because they increased turn down, because when there was just a little bit of flow across, we could control it. But when you have the ability to control really, really, really low flow, then you get into a situation where, well, at what point does it actually completely shut off, right? So you get any kind of debris and that kind of stuff, and you may have a lockup problem. So you need differential pressure with these plates, which is why we put them in the 600 class. Okay, so turn down is a wonderful thing, my point, but also not necessary in a lot of instances. Turn down is oftentimes not necessary when you're flowing really high flow at low differential pressure. But if you had a requirement to increase turn down, which this one, I put some basic parameters up here I'll go through. This one can do up to 1% of its rated capacity. So it can do about 100 to 1 turn down with the right components. But we'll talk about what throttle plates, if you will, what the equivalent of a throttle plate is for these in a minute. Body sizes, 2-inch, 3-inch, 4-inch, and 6-inch. They come in connections which are NPT, flat face and raised face flange in the 2-inch body size. And then in the 3, the 4, and the 6, you have the option of either flat face or raised face. We don't stock the flat face, we only stock raised face, and we have a bunch. So we're ready to answer the mail on the Flomaxes, but we made some predeterminations as to what we thought were the best fits out the door. One of the reasons we're picking that is you don't have an option of a flat face flange and a Mooney flow grid. This FG29 is 150 class raised face flanges. Because we stock the FM1, which has 150 class raised face flanges, they literally have the identical 10-inch overall length. You could spec one or the other in and the body size would not make a difference. Okay, so it'd just simply be a matter of performance. The inlet pressure ranges then that this would work, you could pick it where you had as low as a 3-pound inlet pressure or as high as 250. There is, and this is something that actually I can give you more information on another venue. There now is a high pressure Flomax, 300, 600 class Flomax. So this is no longer the limit, but it is the limit of the standard Flomaxes as I'm describing them and what we stock, okay? But there is an HP Flomax now available. Their outlets then, between 5 inches water column and 247. The reason I picked that is because that's 3-pound differential from the 250 inlet max, okay? So that's typically what you would expect as an outlet range from a Flomax. As I noted, real high capacity, great performance with low differential pressure. That's where you're wanting to put these. And I mentioned the turn down. It's not as good as the flow grid. Sometimes turn down is your enemy, but where you need to span a greater amount of turn down because you have a low flow requirement and you want to make sure it controls well. It doesn't have problems like going on and off and hunting because it's opening and putting so much through that immediately it's trying to close off. So we'll talk about a low flow range extender as an example to deal with that issue that you can put in this valve. All right, some of the differences. Well, some of the similarities, use the exact same pilot. Exact same pilot filters can be utilized. Now let's talk about the differences. When you use this pilot, it's an unloading design, or excuse me, it's a loading design where this is an unloading design. You have to load gas underneath the diaphragm chamber and basically lifts the whole stem up with everything connected to it and takes the plug off of its seat. Okay, so in order to get gas in that chamber, it comes through this outlet port. So just like the flow grid, if this is backed all the way out, then this valve will be closed. But this valve is closed because it automatically loaded gas on top and it's holding it there, say 200 pounds, right? This valve is closed because you have pressure that is on the inlet at 200 pounds trying to get up through the orifice, but it also loaded through a hollow stem, this chamber here that has a piston in it, that's exact same size as that orifice that's pushing down. So it's all balanced out just like this is, but it's all balanced out waiting for the pilot to tell it what to do. The way the pilot tells this one what to do is when the pilot dumps gas in, it's not dumping it off, it's loading it on. It's putting that pressure, when I screw this in, it's putting the inlet pressure underneath the diaphragm to make it get up. Okay, so then, just like the other ones, then I need a sense line that tell the pilot when to shut it off. Notice how this is tubed, okay? This might be a little weird for people. It has the sense port going into the top of this chamber, okay? So let me get it out of the way here a second. Oh, no. Have to loosey righty tighty. No wonder it's not coming off. Okay, there's two chambers on the top of this actuator, you'll notice. And I've got a plug in one of them right there, 1/2-inch port. Okay, so this one that I'm basically taking this line off is another one. Okay, it's a common chamber up here. This is all just gas that would load on top to help close the valve. All right, so the way this is configured with the pilot sense port going into the top, it needs the sense port run downstream from this one. Okay, so it loads that sensed gas from the downstream up here, and then it also tells the pilot what that is. Okay, that's the way this is set up. Do you have to do it that way? No. You could run your sense line just like normal, just like the flow grid, all the way downstream. Okay. This port that we did that connection with would just be plugged. Okay. Well, what would you do with this port then, if that's not going to be the sense port? Well, here's the deal with that's part of the difference between these two. Notice the loading port is plugged. Okay, so here the loading port loaded on top. Here I'm not using it because I'm basically putting gas that's lifting the valve through the outlet. All right, so I don't, this remains plugged. Well, I do have a restrictor. Notice there's not one here. There's no restrictor on the inlet like there is here. But there is a restrictor. But on a loading design, unlike an unloading design where the restriction is before the pilot, in this case, it's fixed and it's after the pilot. There's a pin, a hollow pin right here in this chamber. And what it's constantly doing, just like the restrictor, which is constantly trying to reload gas when the pilot's unloading it, so it's ready to act when the pilot says stop. Same thing's happening here. When the pilot puts gas underneath the diaphragm and lifts up and causes the stem to lift. And by the way, when we do that, this little pin right here is connected to that stem, and it comes up as a valve travel indicator and tells us the valve is open. We'll play with that in a minute so you can see it. Actually, you can see it this way. I've got one right here. Okay, so it's connected in there onto the main stem, and when the valve opens, it lifts up on this pin. Okay, it doesn't lift up that far, but it lifts up so you can tell the valve is open. It's a nice feature that you can have or not have. You can be basically, when you're doing troubleshooting, blind to what the valve is actually doing and just have a cap there. Okay, that would just be called an FM1. Our versions, whether it's an FM1 or the 3-inch or the 4-inch or the 6-inch models, all have the valve travel indicator as stock, just like we've decided that we're going to give this feature to the customers as a standard. If they don't want to pay for it, it's only like $100, then we can put the cap on and take it out. But our standard ones on the shelf all have this added feature of a valve travel indicator to tell you when the valve is off of its seat and when it's not. Okay, so a nice feature. Okay, so because of that restriction that's constantly passing gas to the top and trying to reclose it when the valve is open, we need a place for that gas to recombine with the downstream downstream pressure, which is what happens with a flow grid. I mean, when you dump the gas off the top of the flow grid, it recombines with the downstream and basically is blending with that pressure. So we're wanting to, which is also why this pilot was sensing here, because of that operation. But if we're going to sense from here, we just need to have a return line go into the piping. If this is a worker monitor situation, I have another valve downstream of it, then this upstream regulator would have the sense line run downstream of the second regulator, just like normal in a worker monitor. And I would have this bleed line, this return line, go in between them so that the gas would recombine with what's going to and through the second regulator. Okay, so same thing if this is a relief, because it makes a fantastic relief. This is the way I would do it. I would plug this, forget this thing, plug this, run my sense line upstream, change my cartridge so that it's BPV, right? And in my relief stack, because this is probably facing up, right? It's probably on its side. In the relief stack, I run a return line so that the gas that's coming into this when the relief is open and it's just recombining with the vented gas. Okay, so that's all I would do. A return line into my vent stack here, run my sense line upstream, change my cartridge, and it's a massive relief. It's an awesome relief. Okay, now let's get into the basic things that you need to know to maintain it. You already know about the pilot. The pilots are identical. The rebuild kits are identical. The only thing, like I said, is different is the fact that you're not using the loading port because we're feeding underneath. Okay. To do maintenance on this, it's actually easier than the flow grid if that's possible. Okay. It looks like it's a little bit more complicated, but you never really have to get in to this upper chamber where that gas is pushing down. It's a static change of pressure. And same thing with this diaphragm. It's really not something you really have to mess with. It's not where you have to go in and do like rebuilding. And typically with 150 class regulators, it's not the 150 class regulators that you're typically seeing doing this kind of decompression stuff. It's just like going back to my example about diving. If you had dive tables and you went diving at, say, 33 feet seawater, which is one additional atmosphere of pressure on the diver's body, he could essentially live there forever if he had the air and come to the surface whenever he wanted, and he would never have decompression sickness because there wouldn't be enough additional nitrogen in solution in his tissues to cause him to bend. Wouldn't create that crisis. He has to be deeper with a higher concentration for that to happen. Same thing with these. You're not going to see this kind of destruction typically in soft goods in either one of these if they're in a 150 class type set. So if it's like 60 pounds on the inlet, that's not where you're going to see that. Okay. So anyway, what does need to get maintained on this then? So let's get into that. And hopefully everybody understands that basically these are being set the same way. When I want to check for shut off, I'm just backing this all the way out like we just talked about before. I have my valve that I introduce, flow. I let my inlet pressure come through. I should see this thing be bubble tight shut off, right? So then when I start cranking this down, it puts gas underneath. I see that pin rise. I see that it's starting to work. Now I see flow. I set my pressure and lock my little lock nut in like the other one there. And now I've set it and I'm ready to go. And if it's the worker monitor, the process is exactly the same as I described there too. Okay. All right. So in order to do maintenance on this, we said it was really easy here, right? We just took the loading line off. We got the spring case out. We're able to get to those body spacer O-rings and the diaphragm, inspect them or change them out, put that stuff back together, and we were on with our day. Okay. So with this, I take off. This is a directional body. Okay. So I can still do the left hand and right hand run stuff. What I end up doing is I'm going to flip the top actuator around to put the pilot on this side, but I can never avoid the fact that I have to use this port on the other side, for my filter if I'm using a filter, but take my gas into the pilot. So it's not quite as clean as this where I can change the direction of the body. This has a direction. Okay, just something to keep in mind. All right, so the pilot stays on it, kind of like with the A-mounted Mooney we were talking about before, but with the the added advantage of I got 2 bolts only. Right here's one 3/4 inch bolt. It comes out. And one on the other side I can work on at the same time. I'm going to have to get a wrench on because it's sticking. Oh, there we go. Give it an invitation. Okay. Drew, I probably could use your assistance. Yep. There's an O-ring seal that's keeping the gas from going between the actuator and the body. And that's the real seal. It has a gasket, which if you don't cut the paint on them when they're first new, just go around it with a knife or whatever, and make sure that you cleaned it up. It's not real heavy duty, and it's only a weather seal, but you might tear it. Comes in the rebuild kits. Okay, so you hold there. Okay, so this is the O-ring that's the actual seal. There's that body gasket I just described. Okay, so here is the actual control, if you will, of capacity. This plug retainer on this stem. Notice that I mentioned the stem was hollow. Hollow. Right there. Goes up it straight through there into this chamber, which allows gas to push down. Okay. So if I want to have something less than a CG of 2250, I'm going to see the notches in the stem. I'm going to hold the stem because I don't want to twist it because everything's connected to the diaphragm. I hold that stem with a wrench and I take this nut off. And this is the only place I go for maintenance. Those two bolts that I just mentioned that I took off and this. So sometimes this sticks to the nitrile, you know, you got to kind of gently pry it up. But I take this 100% capacity plug retainer. This is the actual plug seal right here. This is the diaphragm. That does all the work right there of sealing the gas. Okay, so what it's doing, there's a cage in here that just allows pressure to be put down on the orifice to keep it in place when the body's in here. So it's sitting in there like this. Like that. Okay, so the cage doesn't matter orientation, top or bottom. So when I pull the orifice out, this is basically the sealing surface, and it sits down on the edge of that nitrile seat like that. So when it goes in, when this comes down, it's pushing up against that, and that's when it's closed. Okay, so if I want to change the capacity, I can pick a different plug retainer. This is a 25% top end capacity plug retainer. So this is what it would look like. When it's closed around it. But when it opens, when the shaft lifts up and takes the plug retainer away, it can never fully get out of the way of the orifice. Okay, so the only gas can flow around it, but it never gets where it's fully out of the way. So there's your 25%. Okay, this thing is called a low flow range extender. Okay, you notice it has a shape where it kind of like changes from one angle to another on the graduation. When it goes in place, it has a very tight fit around the inside of the orifice for the first like 1/8 of an inch, maybe 1/4 of an inch, and then it gets up out of the way quickly. So what's happening here is that first portion where it's right in that range is the low flow control. It's kind of like the drill hole where it's giving you ability to have kind of like almost like a smaller orifice for a while, and then it gets big so you have all that capacity. So the low flow range extender only takes away about 15% of that top end CG at 2250. So it's still going to give you basically 3-inch capacity, but what it does is it gives you that 100-to-1 turn down, so it's giving you the low flow control. So it's a nice option when that is a needed thing that you can get out of a Flomax. But if you just want to restrict top end capacity because of a relief or whatever, because it has so much capability, you might go to one of these plug retainers. That's a 25, that's 50% capacity plug retainer. This is 75. The LFRX essentially is 85, like I mentioned, and then your standard 100. That is basically no restriction whatsoever once it opens. Okay, so to do maintenance, this is it right here. Take that out, inspect it, make sure that there's no chips, gouges, like wear on the diaphragm or the orifice. And if there is, flip it over. Use the other surface, put it back in there, hold the stem while you're tightening that nut. It's got, again, one of those little rubberized seals on the underside that goes down against the plug seal, plug retainer. Okay, and we're essentially done. Obviously, this is nice to lube this this O-ring before you're putting it back in, because it's going to basically come in here and form a seal. It keeps the gas from escaping where we don't want it to go. We want it to go up through the orifice and out the outlet. And notice there's no way that any of the gas that's coming up through is felt under the diaphragm. The pilot has to tell the valve to put gas under the diaphragm. It doesn't automatically happen like a typical self-operating regulator, where when the pressure comes through, it's being directly felt under the diaphragm. That's not the case. The encasement of where that gas is going to go is completely separate chamber from where the gas is coming through. Okay, and there's a bushing, kind of like the stem guide on that pilot. There's a bushing here that lets the main stem travel up and down off the seat. And look at the top of this. I told you about that valve travel indicator and movement of the shaft. Watch that pin on top. See it come up? That's telling you the valve is open or closed. Okay, and you can hear the gas escaping back through the hollow pin when I let off, because it's putting basically tension on that upper chamber. There's a spring up there, and of course the gas loads to push back. Okay, but it's as simple as that. Okay, putting it back together, I mean, one of the other things to inspect is that this O-ring that's down here where the orifice goes is basically, in a good place, that you have that's where the pocket that it goes in. So the orifice goes down in first. It just sits in the little recess. Then my orifice goes in, and it goes in with the knife edge up, the blunt side down, okay, which fits the O-ring right around it. So it goes down in. Okay, looks like that. Then my little cage, spacer cage, fits down around it, looks like that. Okay. Then, once I gotten this put back together, I'm ready to basically press this back into place. And I'm going to basically try to do it where I'm lining up my bolt holes, and I can just lay that gasket, that body gasket, kind of down where it's going to be. And then push straight down and get it in place. Okay, all right, easy as that. And then I just reconnect these two bolts. Reconnect my two sections of tubing, the inlet tubing and in this particular case, my tubing to the sense port on the top. And I'm done. And of course, if I didn't have the sense line run this way, then I'm reconnecting my tubing to the return line, because I would need that. Okay. Now, one of the things that it's important to understand with a Flomax is, because of the way it operates, and this is in your IOM manual. I don't know, it's probably better to draw or just describe. Okay. Think about a situation with a worker monitor where, with this valve, I'm constantly getting gas when the valve is open, flowing from the underside through this pin to the top side. And then I'm having that recombine by putting that return line in. if this is my sense line instead, okay, like the way that this is tubed up from the factory, this is the way they do it. They put the sense line going into that chamber here, and then you run your sense line downstream. So if this is the sense line going downstream of my second regulator, what if, remember the scenarios we said, oh, well, this isn't either a fail open or a fail closed valve, but it, can you turn that a little bit? But the most likely things that probably will occur is either trash or debris will block the plug and stem sealing on the orifice here, or the diaphragm to throttle plate sealing has an issue. So it's either a body issue there or a pilot issue there. Well, it's really the same case here. If you're going to have the valve not completely lock up, there's either trash between that diaphragm and that plug seal, okay, which actually, because of the way it fits, is pretty hard to do, but possible, and you might get damage there or whatever. But the other place is, what if the plug and stem assembly gets the same kind of wear or trash in here and doesn't completely shut gas off that's feeding underneath? If that's the case, in either case, it's not going to lock up. It's going to be slightly open. And the gas that's lifting here is going to, in that scenario where this is my sense line, and the pilot's told the valve to stay shut, but it isn't because there's gas weeping under here and going through that restrictor pin. Well, it's going to end up going downstream of my second regulator. So that becomes a problem because I've got a path around my regulator. Like say this is the monitor, the downstream one. That's a path around my second regulator if I configure it the way that it's set up now. So we highly recommend anytime that you're either doing a worker monitor or doing a relief, get rid of this. In fact, if you tell us what you're doing, we'll do it for you. I mean, we'll send it to you the way that makes it easiest for you. We'll send this with a stainless steel plug here, allow you to run your sense line from either the upstream or the downstream regulator right from here. And you could use this configuration if it was the downstream reg, that would be fine. You could just run your sense line from here on your downstream reg, but on the upstream reg, we can configure it where you have the ability then to run your return line, run your sense line from the pilot right here, and you're all set. So your upstream reg would look a little different. Okay. So that's basically it with the Flomax. Let's pause for a minute. Is there any questions related to this product, this valve line, before I start talking about filtration and heating for a little while? Anything? Is there anything written there? Nope. Okay. All right. So we run into situations a lot when it comes to pressure cuts on a valve. And now we're going to talk more about a flow grid, really, because unless it's a weather effect, usually a Flomax, being a 150 class regulator, is not going to be subject to icing. Okay, not typically. I mean, if your gas is 60 degrees on the inlet, you need about 400 pounds of a pressure cut to drop the temperature of the gas to freezing and start causing icing. So there's obviously other reasons to protect your valves other than icing when it comes to use of heat. But that's a primary concern when it comes to a flow grid. Is if you're making at least a 400-pound cut, you better be thinking about what you're going to do about icing. Okay, if you regulator turn into a block of ice, you get ice blocking the throttle plate or whatever, it's not going to perform very well. But in general, if you just talk about temperature in gas, particulate starts dropping out of gas when the gas gets colder. So that creates its own problem. Besides the icing, you can have buildup of small particulate inside the pilots that start to restrict, kind of like, block your arteries and your pathways to your heart and stuff when you start having real bad, buildup in your body. So same thing here. if you get those little particulate that basically they attach themselves to things, kind of glue themselves and add on and add on and add on, that can become a problem over time. But you can keep that stuff in the gaseous state if you just keep the gas warming. So typically the 90 degrees is the target to prevent any of those types of problems. And so that has nothing to do with Jules Thompson. You can use that to your advantage anytime. Could use it to your advantage with the Mooney Flow Max in that particular instance. But it would basically be because you were making probably a cut at least of a couple hundred pounds, I would suspect. Okay, so what do you do about it? Well, heating can be applied a variety of ways, as can the filtration. When it comes to heating, what we recommend is a pilot preheater system like this. Okay, so this is from Catco. This is actually an old one that was in our display room. I'll show you in a minute. The high pressure regulators have actually become a little nicer, a little better, and they also have a built-in relief and the additional port that they have. But you have a cabinet like this, and when they talk about catalytic heating, what they're literally talking about is something that, with the help of some voltage, to create a catalyst. So like a hot plate, you know, that you plug in and it gets everything, you know, like keeps your coffee warm or whatever. Okay. Same thing here is this will take gas from your pipeline, just any place you want to take it. Typically it's taken from the upstream side, and you pipe it in and it crosses over the heating pad on the inside of this cabinet, goes through this high pressure regulator to cut it from wherever you got it down to about 75 pounds. So let's say that you took it from the upstream side of this of an FG30, and you had like 500 pounds on the inlet. So 500 pounds will come in. This regulator, which can take inlet pressures all the way up to 5,500 pounds, cuts it to 75. The reason it's crossing through the box right here is because it's pre-warming that gas, because this little regulator is going to be subject to Joule Thompson as well. So we're going to warm the gas to keep this from icing as it does its job. And this second regulator then cuts it down to 4.5 inches water column, some additional filtering, and then it goes into the box at 4.5 inches and creates the fuel that the heating pad is going to use. Okay, so I've got voltage, which will act as a catalyst to heat, basically get the initial heat going, you know, give me a hot plate. I will have fuel come in, and I will have air, which is coming in these vents and coming in the bottom. On the back side of the plate, looks like this. It's a replacement plate with a shutoff valve and thermocouple attached in the same junction box. But the fuel basically is coming in through this port, the air through here, and it's already been heated up by the voltage you applied to this for several minutes. Once that process is going, you can take away your jumper cables or your hookup of whatever that you need to get your voltage to the box. So this is a explosion-proof jumper cables, which they actually thread into that and seal. You plug in the, either port, doesn't matter, there, and then you can just hang these on a post next to them. And then next time that you need to restart it, like you shut the system off in the summertime or whatever, and then come close to wintertime, you restart it if you did something like that seasonally, didn't run 24 hours. But then you have that catalytic process perpetually providing heat at around 120 degrees. And the way that the pilot gets it is, you see these two side connections. Okay, so these come in either what they call single manifold or dual manifold heating units. Take this connection off. So this section of tubing, I've got 4 stainless steel bolts that hold the front of the cabinet on, and basically you can see the underside of the 4 bolts. If I just had to replace the heating pad unit like that, I would just get at it with taking those 4 out. So if you ever had a heating pad go bad, it's as easy as that to just replace it with another one and then put this back on. But there's the heating pad. Inside the box now we can trace what's happening with the gas that's coming to and from it on these 2 side posts. So you can see that it's heat exchange tubing going in front of the heating pad, back and forth, and back out. Okay, and if there was dual manifold, you see these 2 places here, I would have another set that go back and forth, and back out. So I could cover 2 pilots with the same 2667 BTU heater. Okay, if it's a bigger valve, like bigger than 4-inch, you simply use a 5,000 BTU heater to make sure it was adequate for that additional capacity needed to heat it. But here's what happens with it. I take this off, take this section right here off, and I run, instead of having this tube there, I run tubing from here to this point. So tubing goes here into there. Okay, and then it comes out and goes back where the other side was. Okay, so now I get warm gas at 120 degrees, entering my pilot, going through my pilot, loading on top and warming the top of the spring case. Okay, so I'm keeping all of this from icing, keeping the pilot from getting those, flash freezing problems if anything gets in the vent or what have you. So I'm keeping this thing working nice and doing its job, and also keeping particulate out of it. So this is one example, a great example of how we sell Catco regulators with Mooney flow grids all the time, but they tend to be those situations where Joule Thompson is definitely at play. Okay. All right. So any questions on that so far? I'll take just a minute to mention some other ways that Catco can be used, because it's like, so many different types of food, some ethnic food that people enjoy. I don't know, Italian, whatever, where it's just like the same basic components, like a main suite of components put in a variety of different ways to make different dishes, right? So it's the same way with these Catco heaters. All of it's the same. You have heating elements in different sizes in enclosures, and you do different things with them, and you basically start the process with the exact same ways, either AC or DC voltage, and that does the job for you. You can have a heater that goes around, instead of running instant gas into the Moonies, you can put an enclosure with heating around a filter. And so your filter sitting on a stand, and you're running, instead of this pilot filter, you're running your gas into your pilot filter and out of your pilot filter and back into your restrictor, and you're doing all this extra filtering. And you're using an enclosure around it to keep the gas that's entering here warm, instead of it going through and entering the restrictor from this box. They also have them for standalone valves, 627, 630s. They have an enclosure that fits around the body and does the same kind of heating. So they have those. They have line heaters. You just strap like a clamshell around the pipe, and you do your heating of all the gas that's coming through. Okay, so there's a basic formula that applies to trying to determine how many BTUs of heating in these clamshell heaters that you strap on you need. And it's simply this: if you take the number of degrees in Fahrenheit that you want to raise the temperature of the gas, and I'll write this down for you. Okay. So degrees Fahrenheit to raise gas temp. Okay. Times the flow rate in MCFH times 50 equals the BTU rating of the heating pads in the clamshell. So let's say I wanted to raise the temperature of the gas 10 degrees. Okay, I had 10,000 MCFH, and I had that flow factor of 50. So 10 times 10, I'm at 100. 100 times 50, I'm at 50,000. Right? 5,000. So I need 5,000 BTU heater, which basically is just the one I was talking about for a 4-inch pilot heater. It would be the size that it would be, but it would typically be like a 6 by 12-inch heater that would go in this clamshell, and there'd be either one or two to do that kind of heating for you. And of course, it may go up in BTU significantly. You say, well, I don't want to raise the temperature of the gas 10 degrees. I want to raise it 30 degrees, or I want to raise it 40 degrees. So you're making a really massive cut. You may need more heating there to get, you know, back above freezing and that kind of thing. But the point being that there's so many different varieties of these, not just these instrument gas heating boxes are the only solution you can pick. Okay. Let's do real quick then filtration, because I said, well, you know, filtration is at play here too, getting out particulate, keeping it out of the pilot as an example, keeping trash from blowing in and messing up your throttle plate. I mean, these are expensive instruments, and so are your meters that are on those lines. So we don't want to use them as your strainers and filters that you have to keep the, you know, trash out of and degrade their performance and make you have to rebuild them more. So let's take, for example, what you already have on a typical Mooney. Well, a typical Mooney, you have a 30SD or 30AD pilot filter. The AD would just be aluminum, and the D would mean if it has a drain. This one doesn't. This would be a 30A pilot filter, and it has a little polyethylene 10 micron element, okay, that's in there. It works pretty good. It does, you know, a nice job of, like, your only other protection maybe is a Y strainer. Heaven forbid if it's something like this where you're using a strainer gasket. We see these like those restricting orifice plates I was telling you about with the meters. This is not a good solution. People do it because they need space, but there's plenty of instances where this mesh screen, although it's keeping the trash out for a while, gets clogged, creates a new problem for you, or something hits it and actually takes pieces of the stainless steel mesh into the valve and causes it to fail. This is not a good product. We have them because people ask us for them, but that's because, you know, we try to do the best we can to advise, but we're not telling people what to do. This would be another solution, to have like a Mueller or Titan Y strainer in front, and then have for your finer stuff a pilot filter. The Y strainers, the best ones typically you're seeing with, like, you know, 100 mesh screens. 100 mesh roughly relates to about 47 microns. So it's doing a pretty good job of keeping trash out of the body, as long as you have something that's 10 microns helping you keep it out of the pilot. So that's an okay solution as well. Far better, quite frankly, is just put a line filter in front of it that gets you to 10 microns or even 5 microns right off the bat. So run it through there and keep that trash out. There's not a tremendous difference in price between those two products. I mean, this is running at about $1,300. Those will typically run at least $250 to $350, and if they're a higher in ANSI class, much more than that. So this is actually a little upfront cost, but a lot better filtration. So definitely a good solution. But then what about keeping this little better protected? This, again, it's kind of like the Y strainer. It's okay, but look at this, Drew. Yep. Look at this Mooney. Okay, so this Mooney has a Welker F19 filter mounted in place of the Mooney 30 SD filter. Okay, it has 4-micron filtration, and it can also have a cartridge that can have special media in it. So special material that's actually attacking and collecting things that we want captured because they would blow through that other one. This is a canister called sulfur gong, and it basically knocks out H2S. The H2S is terrible because when it gets into this pilot, it starts to like clog everything up. It's like, you know, arterial blockage. Eventually, as it pastes itself all over everything, you're going to have to scrape it back off or change the parts, or you're going to find the downstream pressure, the set point on the pilot keeps lowering and lowering because everything, the pilot orifice size gets closed in and all that. So the first signs of it are, well, you were out there a month ago and you had to set your set point and now it's down 10 pounds. So you crank in a little on the pilot and reset it, and it works that way for a while, and you go out there a couple months later and it's down 10 pounds. So those are definitely indications of something like that happening. But this kind of filtration is good because it's better, first of all, it's better, it's more than double the capture of smaller particles, and it also goes after certain things. It can have silica in it, so you can knock out moisture. It can have charcoal in it, and you can get them in those bigger sizes and just pull them out. This is an F4. And this is nice because, you know, whether you want it custom made by us, I mean, we could even do it on this right here, quite frankly. Just put a couple of Jomar valves so that you can basically, you have your inlet and outlet just like this, you know, this coming from the body, this going to the restrictor. And you can basically open up a bypass, close off your inlet and outlet, blow down the valve, spin this off, change your cartridge, and put your new cartridge in place and never have to stop operating the valve. So those are nice. And of course, the capture of this is, I mean, light years ahead of this thing, okay? So how will you know that this is a problem for you? Well, think about what's going on with this restrictor. We talked about the restrictor. As the hole got smaller, the valve opened faster and it closed slower. So it started giving you an issue where it may cause the pressure after it's supposed to shut off, you know, to rise before you actually see lockup. Well, if this starts getting dirtier and dirtier and dirtier and dirtier, you're going to see differential pressure if you're looking at it that way, but you're also going to see it essentially serving as a restrictor in front of the restrictor. It's going to start to close off the available gas that is loading on top of the valve, and therefore you're going to see those lockup times get slower and less responsive as time goes on. It's going to be a good indication that this is causing a problem for you. A good way to avoid that is to do better filtration. And so that's why we stock this. We actually have different mountings. We have brackets that we use to meet the need of someone that's trying to meet that particular application. So highly recommend the Welker line because of all the stuff that it can do. And it's so easy to mount them on any of the Mooney regulators. Okay, I think it's time to, I think I run my 1 o'clock, time to ask for any final questions or address anything that you guys would like to address. And we're all ears and want to help. What do you got?
Hey, Drew, this is Tony Peterson.
Yeah.
Hey, so I joined in late here, but I do have a question. So I may have missed, and you may have answered this, and I may have missed it, but in your own words, what would be the advantage, or what's the difference between a pilot loaded regulator and just a non-pilot loaded regulator?
Well, if you're talking about this kind of a pilot, you know, we're talking about a Mooney pilot it is serving as an amplification chamber, basically serving as something that gives speed and precision to the body. So it gives you a place where small changes that can be really quickly and easily controlled are making a difference in something that is passing a huge amount of volume, and that kind of thing. So if it's trying to do it directly, it's not going to be able to do it quite as precisely.
So precision and probably response time.
Yes.
What would be some of the drawbacks on pilot loaded? What's some of the stuff that you've seen?
Well, I mean, one of the things that we're talking about right now is you've got to take care of it, right? I mean, it's an instrument. It's got small places. You got to keep trash out of it. You got to keep build up particulate out of it, and you got to, sometimes with those, heating is one way to do it, filtration the other.
Okay. I mean, that was great. I mean, I'm a little rusty, and then I've got some new guys on here too, so it really helps to kind of have a quick overview. So I heard you touch on the restrictor a little bit. So the purpose of that restrictor is to restrict that inlet gas hitting the pilot, correct?
Yes, it's to basically make sure that when the pilot wants to open the valve, that it can do so, because if it wasn't there, then the gas would pass straight through the pilot cartridge and load on top as fast as the pilot tried to dump it off the top of the spring case. So it gives you an ability to adjust the sensitivity and also to make effect on the stability of the valve. So if it's like hunting on and off and that kind of stuff, you can make it, just a little less sensitive if you've got a situation like that. Or if you have a valve that you want to lock up as quickly as possible, you can adjust that restrictor so that it's going to be at a larger number, so there's more gas available to load on top quickly as soon as the pilot shuts off the dump.
So I know there's the little dial indicators and numbers on there. The higher you go in number, what is that more restriction?
No, just the opposite. The higher the number, the bigger the hole. So you're basically making it where it would open slower and close much faster. Okay, because think of it as the gas coming through that restrictor is your closing gas. Okay, it's going straight through and loading on top of the spring case all the time. Okay, so it's putting it in a state of being closed, and it's waiting for the pilot to let it open. So that's constantly happening all the time. And so if it's on a bigger number, it's constantly giving more gas to keep it closed, which means it's going to open slower, because the pilot, when it goes to dump, has to work against that. But if it's on a smaller number toward the min, that means when the pilot dumps gas off the top, there's very little available to work against it. So it opens really quick. But when it hits that set point, it's going to close more gradually than if that restrictor had a bigger number or bigger opening.
So a lower setting would increase response time, right?
To opening.
Pilot response, right?
Yes, to opening. I mean, to lockup. A lower number is going to mean that it opens quicker and closes slower.
Got you. Thank you.
Good questions. Anything else?
That's all I got. Anyone else?
So I know this is a strain trying to do training like this. Was this of the value you were hoping to get out of it? And if not, what else can we do right now?
We order the Welker filter with the Mooney.
Yes, absolutely. If you tell us what it is you want, we can send it to you as an example, like that, instead of with a Mooney 30SD pilot filter. And we use the same drain valve. I mean, so the 30SD drain valves, so I just had one here. Well, I mean, it's this drain valve.
Yeah.
So that can go in the bottom too. So, I mean, those components are essentially the same. But you get, that added pilot filtration. And that's actually like one of the best values because a 30 SD pilot filter is like $450 or something. You're paying maybe 100 more for the F19 with the 4 micron and the bigger capacity, all mounted. So,
David, you had something?
No, I just want to say thank you for doing this for our guys. Appreciate it.
oh, our pleasure.
Hey, Drew, I saw you talk about the Welker pilot heater a little bit. Do you guys care? Do you guys have a schematic or a drawing or something that shows how to tie that into a pilot?
Yes, the Catco, right? The Catco model 2600s. Yes, we do. We have a
What about
schematic.
what about the blue Welker one you talked, or the
Oh.
sorry, the Vortex one? Sorry, the Vortex.
Well, I mean, yeah, for any of those products, if you're interested in Vortex, we have information on that too. So we didn't discuss that, but the Vortex basically is different in that it is kind of like a tornado in a can. It doesn't use the fuel, if you will, from the system to keep a catalytic process taking place. It just does kind of heat exchange between two inner and outer moving spins of gas. And so it works in many instances, but there's some that it doesn't, it's not as broad ranged as the Catco as far as you being able to trust that it'll work in every application. It doesn't do particularly well with worker monitors where it's trying to cover both of those. It doesn't do real good when you have to provide heating to a system where the monitor is set real close to the MAOP, because the returning gas has to go somewhere. It goes basically in at a pressure just above the monitor. So anyway, different considerations with the Vortex versus Catco. The discussion today was really just about the Catco.
How can I get a copy of the diagram for the Catco?
Oh, we can send it to you. You can send it to any request for anything to my email, and we'll take care of you. My email again is Sharrock, JSHARROCK @kgmgas.com. And anything that's like follow-up interest from what we were talking about, be happy to provide. And remember, our website has a lot of the documentation on all this stuff out there too. So, obviously you're.
Appreciate it. Yeah, thank you, Jeff. Sorry, I was calling you Drew because that's what it says. The name of the host is here. So
We're a team.
appreciate
He's to keep me because I'm of the generation that if I wanted to like fix something technically, I'm thinking back to when there were TVs with tubes. And when I didn't get a good picture, I went and banged on it. So he's here to keep me from banging on this stuff right now.
Well, thank you for the information.
Yep, no problem. Well, with that then, it was a pleasure. I wish I could look you in the eye and shake your hand, but I guess that day hopefully is coming soon. So have a good day.
Oh, David, thank you again for your time, and we'll talk to you soon.